Alright, let's look at another case of conservation of energy, this time without the projectiles. Let's dial back on that a little bit. So we got 3 roller coaster carts. They have a combined mass of 1,700 kilos. They're moving through a section of track as shown below. Speed of the roller coaster at position D is 17.5 meters per second. So we would like to find the speed of the roller coaster at position C. Based on the fact that we have information at position D, and we're interested in finding the speed at position C, these are the 2 points where we're going to look at mechanical energy in our statement of conservation of energy. So I'm going to say that my total mechanical energy at point C is going to be equal to my total mechanical energy at point D. So I'm going to have my kinetic at C plus my potential at C is equal to my kinetic at D plus my potential at D. Now, you could certainly change the reference height. You know, you could set the reference height to be where C is at, where D is at, or you could leave it as the ground. I'm just going to leave it as the ground in this case. I like to change it up now and then. Regardless of what reference point you pick, you will get the same answer. And if you don't believe me, try it out yourself. You will get the same answer. If you don't, check in with me. It'll be a calculation error. Now, let's see what we got going on here. So we got half mvc squared plus mghc equals 1/2 mvd squared plus mghd. So we're just writing in our definitions for kinetic energy and potential energy. And this is the lovely thing about doing conservation of energy when there's no springs involved, nor any friction or losses. The mass term is always going to cancel out because I have mass here, 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 and here. It's in every term, so guess what? It gets to go. So we have no mass terms left. That's great. So what I have here is I have this half Vc squared plus GHC equals half Vd squared plus GHD. This simplifies everything nicely. Now I'd like to find the speed at C. I have that half in front. I don't want that, so to get rid of that, we're going to multiply everything by 2. So we're going to multiply this term by 2, this term, and this term. Don't forget when you're multiplying, every single term gets multiplied. So this 2 1/2 will get rid of each other. That 2 1/2 will get rid of each other. So what I have is I have this Vc squared plus 2GHC. This is equal to Vd squared plus 2GHD. So I would like Vc squared on its own. Let's take this 2GHC to the other side. So I'm going to get Vc squared is equal to Vd squared plus 2GHD minus 2GHC. So a lot of work in here, but then Vc, we're just going to square root all this. And remember, when we're taking the square root, we're square rooting the whole thing as one. We're not doing the square roots of each little piece. So we know the speed at D, it's provided in the context. We know G, we know the height at D relative to the ground, it's 1.75 meters. We know the height of C relative to the ground, it's 9 meters. So we're free to get going. It's setting the equation up that's always the hard part in conservation of energy. So we got our 17.5 meters per second squared plus our 2, 9.81 meters per second squared. And then my height at D, 1.75 meters minus 2, 9.81 meters per second squared. And then my height at C, which is 9 meters. Make sure you're really careful with your labeling and your subscripting, because it's very easy to get confused here. So let's see what we got here. So we got 17.5 squared plus 2 times 9.81 times 1.75 minus 2 times 9.81 times 9. So what I'm going to get is I'm going to get about 12.8 meters per second. So what I've been told based on what I have, if I know my speed at D is 17.5 meters per second, at C it's going to be 12.8 meters per second. A good way to check, the higher up you are, the slower your speed should be, because you have more potential energy. You're having more potential energy, and that has to come at a cost of kinetic. The closer you are to the ground, the faster your speed should be, because you have less potential energy getting close to the ground. Then that has to come at the cost of having a gain in potential energy, kinetic energy. So just something to be mindful of. Now we're going to make this problem just a slight bit more difficult. So the roller coaster, it's going to approach the end of the ride at position D. It's going to be stopped by a large hydraulic shock absorber that acts as a spring. So it's going to compress the spring 2.50 meters. So we'd like to find the spring constant of that shock absorber. So what's happening if I kind of go back here? What we're going to have is at D, the carts are going to get here. We're going to have kind of like a spring. And we're going to compress this. This will make this a little bit more challenging. So what we'd like to do, and I'm going to call the spring when it's fully compressed. So I'm going to say when it's fully compressed, that's position E. So what I can say is that my total mechanical energy at E is going to be my mechanical energy. Now I have a choice. I know all the information at C because I just calculated the speed at C, but let's use D here. Because we're given the speed at D, we also know the height at D, and we also know that the spring is uncompressed. So at this point here, spring is not compressed. Whereas for E, the spring is fully compressed. Now that we have a spring involved, this is going to force us a little bit. We are going to have to use elastic potential energy in our equations. Now, the other thing I'm going to do to simplify my life here for this part, as I move between the parts, I can certainly change my reference height to, help me out. But if you're in a problem, like if you're already starting a calculation, you have to stick to that reference height till the end. But if you're starting a new calculation, you're free to change your reference height. Since D and E are on this at the same vertical height, what I'm going to do is I'm going to set this vertical height to be 0. That's going to help me out a little bit later. So at this point, my mechanical energy at D, we're going to have the kinetic energy at D, and we're going to have different forms of potential energy. So we're going to have gravitational potential energy at D, we're going to have elastic potential at D, and then at E we're going to have we may have kinetic energy, and then we have gravitational potential at E, and we also have elastic potential at E. This starts to look, I'm just writing out the full statement of conservation of energy, and this looks really daunting. I promise you we're going to gut that down really quickly. Now, at position D, we have kinetic energy. We are told this thing's moving at 17.5 meters per second. Now, I have set the height of which D and E are at. I've set that as height 0. So we're not going to have any potential energy at this point. We also have the spring's potential energy. So at D, this has not hit the spring yet. The spring has not yet been compressed. So we can also say that the elastic potential at this point is 0. Because the spring is not yet compressed. So there's no energy stored in the spring. We have to actually compress it first for energy to be stored. Alright, now, when the spring is fully compressed, in terms of kinetic energy, we're not going to have any, because this thing is going to come to rest. We also don't have any gravitational potential energy at point E, because we've set that as our reference height equals 0. The spring is fully compressed, so it is now going to have elastic potential energy. So we will have to keep that term. So we've taken something with 6 terms and reduced it down to 2. This is lovely. So my kinetic energy at D is going to be half mv d squared. And my elastic potential energy at E is going to be 1/2 k. And then again, x represents my compression. So the compression of that spring squared. So we are looking for the spring constant. We are looking for this k value here. Now, you'll notice I have a factor of half on each side, so those halves will cancel each other out. So I'm left with mv d squared is equal to kxe squared. Or if I want to find k, then we could divide both sides by xe squared. So what I'm left with is I'm left with k, the spring constant, is mv d squared divided by the compression at E squared. So this really complicated equation got simplified to this. Conservation of energy is a really powerful tool as long as you know how to use it properly. So we know that this roller coaster cart has a mass of 1,700 kilograms. At D, it's traveling 17.5 meters per second. And then at E, we know this thing is compressing the spring by 2.50 meters. We've got to square that. Don't forget your squares. That is where most people go wrong on these questions. So if I do that, I'm really careful with the math. I'm going to get about 8.33 times 10 to the 4. And then my units for spring constant that we talked about a little earlier, it's going to be newtons per meter. So my spring constant for this spring that's going to stop the roller coaster based on the parameters given, it's going to be about 8.33 times 10 to the 4 newtons per meter. So this was a slightly harder question, but with some careful choice of reference point and a few other tricks up our sleeve, we were able to simplify this quite substantially.